discuss two characteristics of point estimates: bias and precision. An estimator is biased if it tends to either overestimate or underestimate the parameter. The precision of an estimator refers to how close it comes to the parameter. Let's take an example. Have you ever noticed that some bathroom scales give you very different weights each time you weigh yourself? Imagine we have two scales. Scale 1 is a high-tech scale that gives almost the same weight every time you weigh yourself, varying very little from weighing to weighing. But this scale consistently tells you that you're slightly heavier than you actually are. So Scale 1 tends to overestimate your weight. Scale 2 is cheap and gives you very different results from weighing to weighing, but it is just as likely to underestimate as overestimate your weight. Sometimes it tells you you're a lot heavier than you actually are, and other times it tells you you're a lot lighter than you actually are. But if you weighed yourself on Scale 2 lots of times, the average would be your actual weight. Which scale do you think is biased? Which do you think is most precise? Scale 1 is biased because it systematically overestimates your actual weight. On average, its measurements are a little higher than your actual weight, but Scale 1 is fairly precise because all the weights it reports are similar. Scale 2, on the other hand, gives unbiased estimates of your weight since it does not systematically overestimate or underestimate your true weight. On a given weighing, it might tell you you're either much heavier or much lighter than you actually are. However, Scale 2 is not very precise. It might give you a shock some days, as its measurements are frequently a long way from your true weight. Let's move on to more formal definitions, but remember the concepts are the same as in our bathroom scale example. When we say a statistic is biased, we mean that the long-term average value of the statistic is not the parameter it is estimating. In our scales example, the statistic is the weight reported by the scale in a single weighing, and the parameter is your true weight. More formally, a statistic is biased if the mean of the sampling distribution of the statistic is not equal to the parameter it is estimating. Think back to what you learned about the sampling distribution of the mean. The mean of the sampling distribution of the mean is the same as the mean of the population from which the scores were sampled. Therefore, the sample mean is an unbiased estimate of the population mean. Any given sample mean may underestimate or overestimate the population mean, but there is no systematic tendency for sample means to either under or overestimate. The formula used to calculate variance in a population is shown here. For example, if we were measuring variance in the weight of a population of college football supporters, we would subtract the mean weight of college football supporters from each individual's weight, square the value, sum those squared values, and divide the answer by the number of college football supporters in our population. We saw in the estimating variance simulation that if n is used in the formula to calculate variance in a sample, then the estimates tend to be too low. What does it mean if there is a tendency to underestimate or overestimate? You've got it. It's biased. But there is a solution. To estimate the population variance from a sample, we use a similar formula, but the denominator is different. We use n-1 instead of n. By using the formula with n-1 in the denominator, we get an unbiased estimate of the population variance. n-1 is the degrees of freedom. Having discussed bias, let's switch back to precision. Do you remember what the definition for precision is? Precision refers to how accurately a statistic estimates a parameter, and it is usually measured by the standard error of the statistic. The smaller the standard error, the more precise the estimate. And conversely, the larger the standard error, the less precise the estimate.